Hello, Sushama. Hello, Sushama.
Yeah, Anita.
Yeah, Sushama, we are online now. Okay, you can start.
Good morning to all. A warm welcome to the second session of the monthly inspirational speaker series by India Electronics and Semiconductor Association at this bright Sunday morning. So it gives me an immense pleasure to introduce you all to Dr. Manoj Kumar. He is Director for Innovation and Partnerships at ST Microelectronics. He has been associated with ST Microelectronics for 24 years in various roles. He is also the member of Executive Council at India Electronics and Semiconductor Association. He is very passionate at bridging the gap between the academia and the industry, and for which he is involved in various activities at both ST Microelectronics and India Electronics and Semiconductor Association. He also leads IESA's core initiative group for talent and skill. A warm welcome, Dr. Manoj Kumar. Over to you.
Thank you, Sushma. You can hear me?
Yes, sir. You're totally audible.
And I will share my screen. Please confirm me once when you have the screen also visible.
Yes.
Is it okay?
Yes, yeah. We can see the screen.
All right.
Thank
Thank
you.
you. Good morning to all, and thank you for joining on this Sunday morning. The topic today is system design beyond proof of concept. The outline of the speech today is to understand what electronic system design is, where is the gap, what are the concepts involved, some challenges and the opportunities therein. I want to build a case that when you talk of system design, it's not only electronics, it's much more than that. And it's not only the design of how the electronics fits into the casing, but also how the electronics fits into the user experience. And then I would give my thoughts about how we could kind of attempt to address some of these gaps. Before I start, I want to make two disclaimers that throughout my speech, I have used the internet resources very liberally, but I have made sure that I have indicated the sources therein. The idea is to illustrate the key messages. This is our slide that IESA, for those who do not know, is India Electronic Semiconductor Association. This is the apex body which advises the government and various other stakeholders on the key electronics and semiconductor policy. So this slide indicates all the blocks that one may think of with respect to the entire value chain of the silicon to electronics. So we think of customer's idea. There is IP and SOC. SOC is system on chip development. There are electronic design automation tools, pre-silicon validation and design. So the upper part is design. And this part is something which is very, very interesting. And in India, we have this skill which is available in plenty. In fact, some people say that about 20% of the design of the entire world, for what concerns the silicon design, is happening from India by Indians. So we are very, very favorably placed for this part. The second is, how do you make the silicon? I mean, it starts from our very humble sand, but then there are processes, material processes, how you make ingots, the wafers, how you let's go to the fabricated wafer, and how do you make the testing. So this part, I mean, moving from silicon wafer to the fabricated wafer on which you can print the design is something that is very, very complex. Today it is nanometer scale. So you have to print the wires, which are in the scale of nanometer, and also spacing between them is in the case of nanometers. So you can imagine that when you have to print such thin lines, if you want, and then also differentiate between them, you can imagine the kind of processes that are needed in between. And as we will move forward, we will have dedicated sessions on all of those. For the speech today, what is important is that this part of printing what is designed in the EDA tools, through the EDA tools, what we call as system on chip, is something that happens in these fabs. And these fabs, because of the complexity that I just highlighted, are very, very costly, and we call them as front-end manufacturing fabs. Once it is done, they need to be packaged, and this packaging part is called back-end packaging, or sometimes let's say set. The speech today is beyond this. So that means you have a chip which looks like this for those who may be very new. So this black portion is what we are talking about. But when you make a system, you do not see this kind of chip. What you see is multiple of them. If you are able to take out the PCB is printed circuit board. So this green stuff is what is PCB. And all these components, here you see that there are some components which are like capacitors, resistors, etc. While we talk of product as primarily electronics, you would see that there are many other passive components which are equally important, and sometimes perhaps even more important than the electronics itself. So this is the portion that I am going to speak today. That means you have somehow arrived at all of these aspects. You have created a chip, and this is about one chip, but then there would be several chips, there would be several let's say components. The combination and permutation of all of those is what makes a end system like mobile, or something that goes into our hearables or televisions or electric meters or cars and etc. I will be speaking on this part. That means somehow you have created a chip first. And then I also highlight one aspect, which is ESDIM, which is called Electronic System Design and Manufacturing. Also, I put I in between, which I call as industrialization, could also be called as imagination. Now, why we are talking of system design today? So we understood when we talk of system, we are talking of systems like mobile phone, like TVs and so on. Before that, there is also interesting aspect to understand that which is the system that one could be designing. I mean, why would you or someone would decide that, okay, I will think of making something for Internet of Things, IoT, or something around edge computing, or something on AR, VR. AR, VR is, let's say, our headsets, for example, as you can see in the picture. So there are studies that happen, and studies are based on certain mega trends. And mega trends could be because how the tastes of the population are changing, how the aging is let's say aging of the population is happening. These result into certain mega trends. So if there are people who are having, let's say, more expectancy of the life, there will be different kind of needs. If there are different kind of needs, how do you address those needs? And primarily these needs could be addressed through the electronics, because electronics has become such a pervasive element that in the end many times we do not even realize that we are using electronics. So anything, everything that happens around us is somehow using electronics, including the webcast that comes to you as we are speaking, as I am speaking. So in the word, this is identified, and in my slide you can see it is identified by a honorable research agency of the world, and they are saying that edge computing, mobile data, IoT, ADAS, here we see autonomous vehicle all around. These are going to be the future trends in the mobility, in the electronics and automation. So all of these are actually the electronic systems, or the part of the system design that I'm talking about. Let's come to India. So there is this report by IESA. IESA is India Electronics Semiconductor Association, as I said before. They have estimated that we would have about $300 billion worth of electronics consumed in the country. So 1 billion, okay, $300 billion. So then you can see the equivalent in the rupees, but let's stay in the billion dollar only. So this is by 2026. On the right side, there are two bubbles. One is, it indicates that in 2021, the market of India semiconductor, if it was this pie or this hexagon, what we were selling from India in order to go into this pie was only 9%. So what it means is that if India is using 100 billion worth of semiconductors, only 9 billion worth of it is being purchased locally. This is how it has to be interpreted. If you scale it to 2026, when we would be at 300 billion US dollars, the share of what is being purchased within the country to make those end systems would be 17% or close to 50 billion. It is interesting for us to understand. First of all, it is good thing that it is increasing from 9% to 17%, or let's say doubling in approximately 5 years, but it is just 9% or 17% of the total volume. Now, there is no need for us to worry too much, but we need to understand why it is happening. And this is where the system design also comes into play. First of all, let's look now globally at what is happening in terms of the electronic design houses, and we will speak of this little later also. I have picked two different reports, and there are, let's say, some names over here, some names over here. The important thing is that there is only one name that appears from India, that is IESA. And that is something to think about, that when you talk of the global design houses, and these design houses are the design houses which would be making the electronic products, no matter, I do not want to name any companies here, but this would mean that the most of the products that we may use in our shoes, for example, in our helmets, or even in our refrigerators and so on, these design houses play a very, very crucial role in suggesting to the OEM. OEM is something who is called original equipment manufacturer, or a brand that we eventually end up, let's say, getting our hands on to. So there are, let's say, these chains, and in one of the slides later, I will be discussing the role of the ODMs with respect to OEMs. Key point on this slide is that in India, we have this situation where we have only 9% being procured locally, but globally, the design houses which are also contributing some portion of that, we have just one name if you have some global ranking. And again, this ranking is not something which is official, but these are two independent reports, but they indicate the essence that I want to share with you. Let's look at mobile phone, because we are talking of systems. So mobile phone is a system from our perspective. And within that, just to understand that all those elements that are indicated are essentially pointing to the electronics that is being used in that. What I want to highlight in this is that beyond electronics, there is casing, there is mechanical assembly, the way each of the elements should fit onto that. All of those parameters are very, very important in terms of the system design. So system design is electronics, but not only. This is the key message. Look at the car. For the car, everything that is displayed over here is consuming electronics. That means there would be one electronic system, electronic module, sub-module that is part of each of the car. In fact, what is important is to notice what is written on the top. A modern car has 100 to 300 electronics parts and increasing. And increasing is equally more important. And this actually starts to tell us the importance of the system design. We are able to, let's say, design the individual ICs for sure, all of them. Navigation system, for example, we have a proud moment of having Navic from India now. The point is that if we have to have more and more bills of material is the term that we use, that all the electronic parts or all the parts, if you were to name each part separately, that is what is bills of material. We are seeing that there is a huge bills of material available for the electronics in a car. So when you make a car, no need to name big companies. We are talking that there are, let's say, electronics that goes into all of those subsystems of the car. And we are talking of this arena today in this talk. Now, let's understand what is the need of the system design, and why we need to understand the needs of the country with respect to the system design. Now, this should start to seem familiar to most of the students who are in class 12 and onwards. At one point in time, you would have worked with some board that is called Arduino or ESPs or Raspberry Pis. You would have, or if it is coming from ST Microelectronics, it would be Nucleo. You would have encountered such boards which have the possibility that you could go on extending their height if you want, but within the height, each of the board could have a independent function. And usually the board at the bottom is the one that is what we call as microcontroller, could be microprocessor in certain other situations. This would mean that you are able to compute and then you are able to add one function at a time. So you could add a function, for example, for sensing. You could add a function, for example, for imaging or camera, or you could add a function that is able to tell you the GPS location. So all those things, if you could go on adding, then you could actually determine everything with such boards if these boards are available collectively or individually. What happens today is that each of the company, independent of the company, but that is into this kind of business, would provide you the tools, not only these hardware tools, but also the associated software tool. And then you are able to kind of integrate the functionality of each of the add-on board that you are doing. And this is what we call usually as a proof of concept. It may sound strange, but if you were to think of for example, a wristband, you are able to simulate or exactly design using this. And you can actually design a software that is pretty much to go even into the smaller form factor. That is the power of these boards. And this is what we call as proof of concept. That means you get the board and maybe design one intermediate board by yourself and you get the functionality. So this is something that we have been doing. We are very good at as a country, as individuals. In fact, I have seen that with the concept of block programming, that means you don't even need to program in C. There are students which are just in class 8 and sometimes even below who are able to program and run their programs, who are able to program into the microcontroller and run it just by the English language. That is what I'm trying to say. That's a good thing, really very, very good thing, amazing, and we are doing amazing job in that as a country, as a whole. Let me just illustrate few examples that what we are able to achieve with these isolated boards. Here you see a robot. Chandrayaan would be in our recent memory. You could make all these fun-loving gadgets using these individual boards that you saw. If you want to make something more professional, then you could see on the right side where you see that these individual boards can be put to the use that you could go not only in one direction but multiple directions as you want. Note that inside you still are having those individual boards what I was speaking before. And these boards are very, very useful that you can create a proof of concept. And if you have the real estate, or let me put differently, an area available, many a times these boards would be covered by the body, which is, let's say, large enough, and no one would be able to know from outside if there are, let's say, proof of concept boards inside, or someone has, let's say, taken further step also. And sometimes you would see that the small companies are able to survive just like this. That means you buy something which is available from market, you do your value addition, and then you sell the product by your own brand. Nothing wrong there, nothing against anyone. The problem is that when we start to make a board or a system which looks like this, you look at the parts. These are the real parts. I have removed the name in the bills of material. Usually you have the name of the supplier also. That's not the intent here. Intent here is that in this kind of board, what you need in the end is microcontroller, some memory, some connected board, etc., etc. But what all it is having all those extra stuff which you do not need in the end application. So that means if you were to design your application, your system like this, not only it is looking bulky, also it is using unnecessary components which are not required by you in the end. What is required by you in the end is a subset of all of that, and that requires you to make another. And this is where the focus that I would, let's say, like to bring in today. I want to highlight that as a country, again, I'm speaking us as a country, that thanks to the fact that companies like mine, they will provide all of those building blocks to the extent that we can start with the device prototype, as I explained in a couple of slides. The problem is that when you have to make a form factor board, and why you have to make a form factor board, you do not want the extra fat that is there available on each of them. But there is something more. These boards have been designed by the organization to promote certain products that are on them. And that means they are many times even over designed. Why you would need all those connectors that are there? This is just one content. then there would be, let's say, many other parts that are not needed. Worst, these boards are designed to work in very, very different conditions, whereas your condition could be either much less worse or even worse than what these boards were designed for. And when we make use of these prototypes, what we end up doing is what those manufacturer of different boards had intended for. And when you bring your bills of material to the level that you want to make your own board, at this stage, there are multiple changes that happen. Because a board that was very comfortably working, you unpacked it and you saw some user manual and it was working, and I claimed I have made a home surveillance system. I am able to see from the cloud. I am able to put a GPS on my car or bike, or I can make a alarm system. All of that, what you were able to make using what is there on the left side, that doesn't happen the moment you shrink it. And this is something where we as a country, we need to think, we need to introspect also where is this art and why this art is not so much in the country. And beyond the form factor board, there is something else, which is the final product. Look at it. If you have to put something into a glass, like the one that I'm wearing, imagine the kind of requirements that come on the form factor. It has to be form factor board, but also the conformal one. And in the end, despite the fact that you may make something, there is user experience on the market. In the end, user also has to like it. This thing that appears in this rectangle is the focus of the discussion today, and I want to highlight. In fact, there is nothing that we can teach in 30 minutes, 40 minutes situation. The idea is only to highlight what is missing here and what are the opportunities and what are the challenges. Moving forward, I want to illustrate this through an example. This example is an example of a wristband that was required to be made, and here the requirement was that you should have a wristband that you can wake up through a mobile phone. So there is NFC, what is called as near field communication. That means you bring two coils in the vicinity of each one, and then they have this magnetic field transfer. This is what it means. So the idea is that when you have this wristband, which is having a microcontroller inside, and microcontroller has the possibility that you can wake up through certain wake up pin. So the wake up mechanism could be, let's say, activated by bringing a mobile phone in the proximity through this near field communication or NFC communication. This was the requirement, and the requirement was just a trade fair where this must last for at least 8 hours. And when you do this, someone who comes to your booth, he wears it, and every time you go, okay, you touch it, and then you have the, let's say, you are registered on the different counter, but also you have the description of the product of the booth and so on. This was the requirement. So this is how we start with the end in mind. But when you start it, one is that you could have done what was available as several prototypes, what I showed, that you have codes, and then you can do it in the matter of hours or days, perhaps, if you are expert. The point is now you have to shrink it, and when you shrink it, you start with what could be available. I mean, unless you design your own die also, I mean the casing also. Usually for such a thing, you would start with what is available. So these are the steps available. There is something that is available. That means now you are limited. Your PCB size is limited by what is the available size. So we arrive at some of these things, but all of these should also have a battery, and this battery should also be rechargeable, and then this battery must also fit into this casing, and casing in turn must fit into the wristband. So this is just to give you some glimpse of the requirement of the system design through the most simple exercise that could be there. And then there is a need that there should be an app where the user could keep track of himself as to which all booths he had visited and so on. Moving on, so you start with end in mind and you create something, as I said before. Then you come to the PCB. PCB is printed circuit board, just to say. Then you populate the components, or let's say decide where each of the components should go. And there is a definite amount of engineering that goes into this, because on the board that you received from the market, something was placed by someone who had designed that board as per the requirement of that board. Now you are deciding the requirements, so you have to decide everything, not only where a microcontroller, for example, should be, but also how its orientation should be. For example, if you are having USB charging on this side, this is a simple thing, but intuitive, and we do not understand its importance unless we design one board by ourselves. This is a key point that I want to highlight. And of course, then there are needs of programming, and after you program, you don't need this big thing, so you kind of break it and so on. All right, so this was designed, And then there was this interesting situation that if there is a near field communication, it must be communicated through the antenna. So you have, let's say, certain number of turns that you could have in order to increase the gain and so on. Once you do that, you understand that there is also some material that is beyond this, which is kind of limiting it. What do you do? At some stage it was inside, so you need to bring it outside this casing, outside the white casing, still inside the black casing or red casing if wristband was of, let's say, red color. So these are multiple iterations that happen during the entire journey of system design, even for such a simple wristband, which we call as pedometer. And now it is perhaps not even sold as a separate device. This is just to illustrate the content. There is something more, that when you make even such a system which is just, let's say, 1,000 pieces or 2,500, it is manufactured in a facility, and that facility, we want that each of those 2,500 let's say such units should be working. That means they need to test it after it is manufactured and packaged. Now the requirement is that, okay, we are ready to test, but then the testing time should not be more than, let's say, 10 seconds for each of the devices. Otherwise there is a cost added. Now again, you have to think like, so it is none of this is part of your actual wristband. I mean, you don't bother if there was a factory which was taking 10 seconds to test it or 10 minutes. But when you are thinking of the system design, each extra second spent by you, each extra layer of the PCB introduced by you, each extra element introduced by you has a cost. So it's a cost versus performance trade-off, not only throughout the life cycle of the product, but also when you are, let's say, manufacturing it, even in the limited quantities. Of course, then this is the final. So summary over here is that system design is much more than a proof of concept, and all of this, what I showed, when the starting point was already a proof of idea. Moving on, and I'll be a little fast here. This is another example where you have these kind of boards which are having, let's say, Bluetooth, and Bluetooth has certain characteristics that I cannot explain here. But imagine that if there are, let's say, two RF devices which are in the close proximity, both of them are able to transmit and receive, then based on the RSSI or other similar values, you are able to understand how far is the other device. And this characteristic was used to find the distance between two such devices if these devices were to be worn by the people. And this was a necessity during the recent black years of the COVID. And of course, we demonstrated it through such a board, but then there are organizations which would have such kind of business model. They can, let's say, create the final systems that are much better than that you can hope to design. So this is such a big board that this goes nicely into a wristwatch, and this is the name of the company that kind of designed it and sold it. The idea was that if there is another person which is within 2 meters of your vicinity, there would be some kind of LED flash, but also it will be vibrating, because thanks to the fact that there is a possibility to vibrate it very easily. Now, with these two examples, I want to summarize that what are the important aspects of moving from proof of concept. I think we understood why it is necessary to move away and move beyond the proof of concept. We need to minimize everything, whereas maximizing the user experience. This is what system design is. I told you that you could make proof of concept. You have ready code snippets. Use that. Then comes the question of code optimization. Imagine that on the board, on the POC board, you have the, let me call it a microcontroller, which was oversized for your application. So you have a PCB, printed circuit board, which is, and maybe you have a organization from where you are buying these microcontrollers that can give you the possibility that you could have, let's say, 64 KB, 128 KB, or 256 KB, or depending on the application, let's say, different memory sizes on the same periphery or same number of pins. If this would be the case, your choice would be to really optimize the code. What you received from the web, from your proof of concept, may not be the most optimized code, because you can use a device which is having lesser memory, which is sufficient for your application, but it is much lesser than what was available on the POC. And so on. Then comes the area and size optimization, but also the cost optimization. Cost optimization could also be how many number of layers are in the PCB. If you have to reduce it, you increase the number of layers in the PCB, but then the cost of the PCB also increases. So there is a trade-off, depending on if it is a consumer electronics device to be worn on a wristband, or maybe a patch for the heart and so on, or maybe it is a wall-mounted device. So the considerations would be different. Size of the components would again be different, and size of the component would mean if you are using very small sized components, that means the assembly cost, the soldering cost would increase later, or maybe you are happy with using the traditional sized components which are little bigger in size and so on. So manufacturing costs are, let's say, decided based on that. What is happening as a result of all these trade-offs? There is no particular theory that someone would be teaching you. This comes with the experience, and this experience is something that we are not getting because we are happy at the POC level itself. And this is the gap that I want to highlight to you. Again, just starting from the beginning, we said that in India, there is about 9% of the semiconductor that is purchased locally for what is produced locally or what is consumed locally. And then now I'm starting to connect it with the fact that many of these designs are actually coming from the external world, and sometimes external world means outside India. And many a times the finished products are coming from outside. And one reason for that is that we do not miniaturize enough by ourselves. When I say enough, it's not to say that we are not able to make it small, but enough number of miniaturizations are not happening in the country. Recall that I told you, out of the top 10 design houses in the world, we have just one. That too, in my opinion, is there in the list because it has a large North American presence. Nothing against that. It is just to say that why even one is there. It is also thanks to the fact that it is present in North America. If it wasn't there, probably we have zero. I'm not talking about the fact that there is no design house in the country. This is not the point. It's not in the top 10. That's the point. Battery life and power management is another critical situation, because when you are making the concept, there is no problem. You have power supplies, you have benches, you have USB from the laptop and everywhere. But in the end, how it has to run. But not only battery life, the battery also swells with the usage. So you have to think which kind of casing is there, which kind of heat management is happening over there. So summarizing then, lab to fab is a multidisciplinary approach, and system designer needs to acquire several different roles. And this is another point, that it's not to say that one person needs to acquire all these roles or all these jobs by himself, but we should understand what is the job that is important from the adjacent team. It so happens many times that if we are a coder, we believe that coding is the most important job in the world, which is good, as long as we have similar respect for another job. That could be layout, that could be mechanical assembly, that could be 3D assembly, 3D packaging. And many a times we have seen, and I have personally seen, that particularly entrepreneurs in the beginning make this mistake, because one person who has the idea, he can say idea is most important, and it is. Someone who is doing electronics, he would say electronics is most important. Something with the software is most important. And if we are able to match these most important elements by understanding the importance of each, that's where I think we succeed as system designers. Other factors are, of course, the tolerances of the component, because not only electronics is important. Passive components, for example, if there is a, let's take resistor or capacitor, which is, let's say, with 1% tolerance, and to save cost, you are using something which is 5% tolerant, then you see that the performance is changed, and then you start wondering, my POC was working fantastic. I was doing everything, even in, let's say, cold weather or very warm weather, but now this is not working because we did not take care of the tolerances and so on. So I won't speak about everything. I am just looking at time now. Okay. And then let's look at what is happening in a wearable watch. The situation goes on becoming more and more complex. I explained you through the wristband. The situation goes on becoming complex. Now let's look at creating a final system illustrated through a smartwatch. You start with schematic, you create a PCB layout, you create a final form factor PCB itself. Then there is a development environment, there is integrated development environment, there is app if needed. What is often less forgotten is that there is a very, very important role of the instrumentation, debugging, and really qualifying the system for certain kind of market. For example, there may be need of CE certification in some, FCC in another, and so on. And finally, you have to see that the form factor PCB must fit into the slot that is there, and then you are able to call through your mobile phone and so on. All these steps are very, very important in the journey. Now, introspect yourself when you are thinking of a smartwatch. Which is the brand that comes to your mind? Next question, how many of the brands are from India? Move on. All right, this slide I have left intentionally blank. And the reason was exactly to have you thinking that how many products that you are using are designed and owned by Indian companies and what could be the reason. All right, let's come to the reason. And the reason could lie perhaps in industrialization and imagination. We, as I said, I repeat, we make fantastic POCs, fantastic software, optimized or not is different situation. When it comes to really making a small form factor board which will last for years and thinking of the life cycle of the product, this is where we need to work a little bit as a country. Again, I want to just bring another aspect that as semiconductor companies, you would have these kind of devices, you would have these kind of eval boards, sometimes you may have a system eval. System eval is that multiple functionality of these eval boards are put onto one. Still, it is much costlier because the purpose of the system evaluation is not to sell it. But sometimes there are modules also that could come from some silicon companies. The point is this form factor board that fits into the final requirement is something that is not only about shrinking the size, but also understanding the market needs, market behaviors. You understand even the kind of strap that starts to matter, not only the display. And all of this is coming from the people who are not necessarily electronics. And that is something that is another important aspect of the system design, that you need to have respect for all the competencies that you may not have. And that's another trick that we should keep in mind. Same is the situation over here. We need to understand really our customer need. For example, these devices may be used in fans, including railway fan. The point is how this railway fan is used. One is, of course, railways will take care of that, but as system designer, particularly electronic system designer, it's also important for us to understand how the end product will be used so that we can work backwards and incorporate the stuff into our own designs, which can help the railway and the users of the railways in the end. Last segment, let's look at, and I'll be fast here, wearable assembly. I think we are familiar with these kind of devices. These are gaming headsets that you are having some controllers in your hands. These are different sub-assemblies that you have. There is a camera positioning, front camera, adjusting strap, and so on. There is a charging headphone jack. So everything has a reason to be where it is. And this is coming from the system design. If you just explore the PCB, you see there are controllers, flexible PCB. I mean, if something is on this periphery, the PCB is no more, let's say, two-dimensional or three-dimensional. It is flexible also. That means you are able to make the shape that you want, and it fits nicely. And that brings in several, let's say, disciplines into picture. Electronics can be on the periphery, as we said. And finally, if you look at it, there are, let's say, mechanical dimensions which are as important besides the placement. So placement starts to become actually even more important than the design of the electronics itself. Because when you go into the product design, you would hit a situation where probably electronics design could be available from some design house, but to be able to map the consumer behavior, and consumer behavior is not only consumer behavioral dynamics, how the hand moves, how the right hand moves, what are the reactions that happen in the body when you are having, let's say, gaming controller. All those things need to be modeled into the physical electronic devices through the software, through the application, and then it has to be average of all the behaviors. Because you have to think of the fact that maybe there are, let's say, millions of users. So what is the average of those millions of users? You cannot go to million users. Then you need to understand what is the research that is coming. So I hope I am able to explain myself what is all that is system design. And with this, you can see that the electronics actually starts to appear a simpler subset of the entire electronics. I have, let's say, masked some of the areas because the idea is not to highlight what is inside. The idea is to say that what is the kind of complexity. So several different PCBs consisting of even IC dies. when you succeed, if there is a large volume, you don't even necessarily work with the finished semiconductor devices. Maybe you would like to have die because you would like to reduce the thickness further. If there is a package of the IC, there is a finite thickness, even if it is in mm, but perhaps an mm is too much for you, so you would like to go for die. And that means you are working very, very closely with the semiconductor vendor, which is able to supply you the dies also, and so on. So summarizing, system design is about having knowledge of several different boards, several sensors, several devices put together, resistor, capacitor, amp, everything. Do not forget the mechanical part of it. Screws are as important as everything else. And that is where you end up, let's say, creating a device like AR headset or VR headset. And with that, this is where you use it in the end. You have the user experience that starts to become more important. So it's a multidisciplinary knowledge and user behavior understanding, which are very, very important ingredients for the system design. I want to take a pause here and show you something over here. You may not be able to hear the audio, but I will explain. When we think of building a semiconductor nation, it's not only what one person, one company can do, it requires involvement of the society. And here I take an example from another country. The country happens to be Israel. Yeah. Right? That you suggesting, I didn't imagine all these people donated, people built, they built it without, this is all criminals. Okay, probably you couldn't hear the audio. What it was being told to me was that everything that you see over here is free. People are building this stuff by themselves using what is available. But also there is this kind of person who is resident over there. This is an old man in a positive sense. That means someone who has worked in some companies, several companies in the past. Now he's retired, but he comes here for his own interest. But he is available to teach kids also if they are needing, let's say, some more help. The place is a fab lab. I don't want to go into the details of the fab lab, but consider it's a place where anyone can go and experiment his idea. This is happening in a building that is by the government, but all the equipment inside is donated by the public at large. Look at the right side. Someone donated the machine, and someone here fixed it and made sure that it's working. You can come and build your own. Someone donated this machine. That is what this person is telling me. Someone donated this machine, someone fixed it here, and this machine can be used by anyone who wants. And those who can identify this is interesting, let's say, soldering machine that we can, let's say, try to understand. Key message over here is that it's not just the government that can build a semiconductor nation or electronic nation. Society also needs to come forward. Government can provide some facilities, but perhaps people who have large amount of experience who are retiring also from electronics, from semiconductor companies, they could become coaches in their respective cities, and we could have a movement at universities level, at district level. Think of the district libraries that we used to have, perhaps even now. So we could have this kind of district centers where people from that district could come, someone who is volunteering his effort because he is retired, but he would like to be, let's say, stay engaged in. This is one way to think of building the nation, and this is not something that is fictitious. It is happening in one of our friendly country called Israel. Finally, if I talk of POC and beyond, the key takeaways are that the building blocks for the demos are available as proof of concept already from the companies like us, but many other companies. And these are sufficient for making a reliable software and firmware which works in the final product also. Of course, you need to optimize, but POC to final product is a tedious, less taught, and much less experienced journey. And through my slides today, speech today, this is what I try to share. And my suggestion today is that each one of us who is in the electronics field, we can pledge to make a board by ourselves. What is coming as proof of concept are the ready-made board, made somewhere in Poland if you want, or US or wherever. We just make one. If we fail, we would learn even more. The idea is that we would at least appreciate that what we see as finished product is not so easy to make. And once we are able to convert that into the movement, we would truly have a semiconductor nation. And let's not forget the last part, that really system design is a multidisciplinary approach. If you are talking of a healthcare application, you have to collaborate with the hospitals. If you're talking of space applications, there is ISRO fantastic, and so on. Last point is that system design is not only about shrinking the PCBs, it is also about thinking of the new systems of chips. And this is something that is happening in the country. And with that, I really end my speech here, and I look forward to any further questions. Thank you for staying for this.
Thank you, Dr. Manoj Kumar, for this insightful session and for walking all our viewers and us to this journey of, to a section of this journey of Santo Electronics, where we have told them about the proof of concept and beyond, and give them a deep dive or brief deep dive into this sector. Like taking this discussion to next step, I'll just request few questions from you to you. So maybe I'll start with the pledge which you urged to take all of us and take this POC forward to the production stage. So, sir, like if I may ask that, what are the typical steps that are to be taken when we when we take this proof of concept to the production level? So if you can share those typical steps with us, with the viewers, with the students, with all around.
Well, I would admit that I have limited experience. There may be someone in the audience who has much more capability to answer this question. But based on my capability, from the proof of concept, of course, you have to understand what exactly you need. You come to the schematic level. And when you are at the schematic level, there is no need to go to the PCB before you decide the bills of material stuff. That means one is that you can make the PCB. The point is the component should also be available. Then you have to think of the fact that if you make a PCB, would it be made by someone, and how many numbers, what would be the, let's say, cost of the material, cost of the components, and what are the, let's say, supply chain constraints. There is a need for you. Let's say if you are an entrepreneur, if you think like an entrepreneur, maybe you would like to introduce, I don't know, hearable device or something for the healthcare. Maybe you have 5-year horizon in mind. You create something which works very nicely, and somehow you succeed in the market. And after 6 months, you suddenly have this feeling that one of the suppliers says that, okay, I am terminating this. So those are the things that you have to take into account, not only that's a building, so you have to think of the resilience, the tolerances, but also the longevity of the partnership. And this would also mean that we have to kind of think long term also when we think of the system design, in terms of the partner, in terms of software, in terms of the code optimization, and all the vendors in the supply chain management. That is what comes to my mind to your question.
Thank you so much. Maybe the next.
Another comment, and probably it is also important to understand that we don't need to do everything by ourselves. I mean, let's align with the people who are available to help, and do not expect any help for free. I mean, you have to pay, but sometimes paying is much better than, let's say, struggling by yourself, considering some aspect to be very, very trivial, and learning it after, let's say, wasting some 6 months, sometimes 1 year, and sometimes being in a situation where you have to abandon the entire idea because it has become too costly.
Thank you so much. So I'll just take one question from our viewers. So he is asking, what happens when AI becomes efficient in semiconductor industry, like in fab part and further verification, as it becomes more better and better than human? So
yeah, this is an interesting and ongoing challenge. I think AI is offering some convenience. It is able to do repetitive jobs. Some claim that it will be able to supersede human beings also. I cannot comment if it will happen or not, but I think that era could be a little bit far away. I believe that creativity of the human beings is very, very deep, very, very deep. More you challenge, more you get back. More you challenge, more you get back. And same could be true for AI, so it could be continuous race.
thank you. So there is one question from. So this question was from Nine Para. I don't know what his name is. So, but yeah, it's Nine Para in the chat box. So the one question is from Ketan Patel. So he is saying that I am zero in this field, but I am interested to do PhD in this field. So how should I start?
Very good. And if there is someone who is also evaluating the PhDs, I will answer for them also. Very nice question. I think, first of all, this field is capable of producing not one, but several tens to hundreds of PhDs. That is the first one. PhD is one thing, I respect that. Imagine that if you are able to create a company by yourself, not to compare each other, but at that point, you could hire several PhDs as well. So it is such a power of the system design. And as I said that if you want to, let's say, start, you start in the ways that I described. There are, let's say, proof of concept systems available. Anyone can start. As I said that today, children are able to let's say play with the code, with the boards and so on. So depending on where you are, I think today, even if you are staying in a village or city is not a limitation anymore. And thanks to all the aspects that you could buy anything from anywhere, and internet has democratized the information to the extent that if you are really willing and interested, you can find this information in any corner of the world. So the starting point would remain what I said in my presentation, and then ending point would be really characterization. And those who are evaluating PhDs, if they are evaluating only on proof of concept, I will also nudge them. Maybe ask one question: did you stay only with the proof of concept modes, or you also tried to make one? I'm not suggesting to penalize anyone. Let's start with that, because we need to nudge everyone as a society together. And then I think we will have many such PhDs, but also many such theses coming out with the real systems.
Thank you, sir. So we have another question from Jeevan Malik. So he is a student of MTech EC VLSI System Design, first semester. So his question is, what are some of the tools we should be handy with for VLSI?
Well, for VLSI, since you are already into the MTech part of VLSI, so you can go to your own lab. Because here, if I say some tools, that could mean promotion. I do not want to say, but in our India, there are three major companies: Cadence, Synopsys, and Siemens. I think they are providing all the tools. So depending on what is your appetite for the IP, SOC, there are EDA tools from each one of them. But there are also some free tools. There are some free tools also, but free tools will not take you too far, but sometimes could be good enough to start learning. If you are, let's say, from the beginner level, if you want to do something by yourself, there are, let's say, free tools as well. But otherwise, there are three main vendors, and I think between them, they cover the entire spectrum of all the Indian universities. And they are providing the tools for the PCB design as well, something that I was speaking in my speech.
Thank you. So we have one question about digital image processing. So this is Kumat. I'll just say Mr. Reddy, because words are combined together, so it's a little difficult for me to read. So I'll just say him Mr. Reddy. So he's a electronics background student who is studying in the final year. So he's asking what you say about digital image processing.
Well, I think digital image processing is something that is giving us more and more creative options, particularly intelligence at the edge. We are talking of AI, then AI at the edge. If you look at it, AI at the edge is largely image driven. Of course, you can say there are humidity, pressure, temperature, and other kind of sensors, presence detection, and so on. But primarily, AI at the edge is about the image. For example, imagine that you have a situation that you would like to understand if a certain vehicle is going passing after some good deed or bad deed. You are able to do all of those things only through the image processing. And if your idea is about further into the IC design of the image processing, I think that requires much longer answer and perhaps even beyond my capability.
So I think all of them has typed thank you, and maybe I'll just repeat.
Any other question?
Excel in this field of system design and make most out of this POC experience. So some advice for the students which you can share with us.
I wasn't able to hear or see you for a while. Can you repeat?
Oh, okay. So
And
am I?
now
Am
you
I?
are perfect. Yes, please
Okay.
ask the question.
Okay, so I'll just ask one question, that what advice would you give to the students who want to excel in this field of system design and to make most of out of their this POC experience? Like there's
I
what
would
I'm
advise each one to create at least go beyond the breadboard. I mean, that is the first thing. Go beyond, let's say, putting the wires. When I say wires, I have one system kept over there. It is just what I showed. That is just to illustrate this thing, but go beyond this. Try to optimize. I mean, look at each of the board, find its bills of material, and you look at your own system, how much of that is extra. You would discover that maybe it is more than 50%. More than 50%. Make one PCB, build the components. Buying the components itself is an experience. As a matter of fact, it's not entirely to blame students or ourselves as a country. In some other country across Himalayas, we have the situation that any component that you want is available very easily. This is not the situation here. So this is also a situation that needs to be addressed by the government. So I would only say that make an experiment, try to understand which are the vendors, and the identification of the vendors where all you could get it developed. It itself is a very enriching knowledge, and then making one PCB a system, testing it, debugging it, seeing it working is very empowering journey. It is an experience that you can't explain by words. You can only have it. Imagine that if one of you or some of you would succeed in creating some companies in some years from now that could become brands in India, global brands. Look at the amount of satisfaction that you can have. And that is what we should strive for. And that is my message. And this is my message not only to the students, but also to their parents, also to the teachers, also to the researchers, that we look at this field which is little bit less neglected because of the fact also that perhaps it is not so costly also. I mean, if you look at the fab, you talk of $5 billion plus investment. These things could be addressed by much lesser cost, but there is a problem and reason for that. We talked of the EDA companies. When there are EDA companies, they go because there is a big license fee that can happen. So there is a reason for them to go. But for the system design, it is not as expensive, and there are not many people who are telling about it. And we are silently suffering without realizing what is happening. And probably there is no one who is advising government or the people who are policymakers enough about its importance. I mean, we should have a situation like we have a coffee bar in each university. We should have one component bar in each university. And that's my visualization, but also message is that you create one system by yourself. Forget optimization in the first case. If it is working, simply because you put everything even in two layer or one layer or whatever, you through whole component, don't worry. Make one. That's my advice.
Thank you so much, Dr. Manoj Kumar. So, with keeping in mind the time, so it has indeed been a very insightful journey. This 1 hour was certainly something which I enjoyed. I hope even our viewers must have enjoyed, because the way the students are asking the questions, the people are getting interested. Maybe if you have a few questions which we will take offline, because we don't want to exceed the time limit. So thank you so much, Dr. Manoj Kumar. Thank you so much, everyone here, and see you all again in the next Sunday, in the first Sunday of the next month. So please be stay tuned. We'll give you an update on what's happening next. what we'll talk about in the next session. So please stay tuned. Please be with us, and thank you all for your cooperation and for your support for this and being a part of for this session. So thank you so much.
Thank you all for giving your 1 hour on this precious Sunday. Bye bye.
Thank you.